Thank you, Dave, for the kind introduction. Thank you for coming to my talk. Those of you who are familiar with optical communications, I can summarize what I'm going to say in one sentence. I'm going to put the information in the scattering data. That's it. Okay? For the rest of you who don't know what that means, my talk will elaborate on that. Let me begin by first thanking my collaborators. Mansour Yousefi and Siddharth Hari were our former PhD students of mine. Gerhard Kramer is a collaborator at Technical University of Munich. Alan Lau works in Hong Kong and was the professor in charge of the equipment in which we ran some experiments on an optical test bed. And René Essiambra is a researcher at Nokia Bell Labs. And thank you, Dave, for inviting me to this auspicious occasion. So this first part is more or less a tutorial. For many people working in information theory, the fiber optic channel is kind of a foreign one. It's a little bit different than the kinds of channels we're used to dealing with. And so I want to kind of highlight how we sort of deal with this fiber optic channel without actually doing physical experiments, so on the computer. Here's a map of the world, just showing that fibers are very important. This just shows the undersea cables connecting up the world. All of the continents, of course, are crisscrossed with a spider's web of fibers. These are the major undersea cables as of 2012. And you can see, of course, that all of us use fiber optic communications every day whenever we want to access a bit that's stored on a server somewhere remote from us, maybe across the world or even across town. Okay? You're using fiber for probably 99% of the data that you're sending, even in communicating in wireless. Okay? It really is only wireless to the base station, after which it gets converted to an optical signal and sent. Okay? So, fiber optic communications is a miraculous triumph of physics. Physicists, first of all, developed amazingly transparent glass, which loses only 0.2 dB of its energy per kilometer of length along the fiber. Okay? Which means that after 15 kilometers, say, you've lost only 3 dB, or half the power is still there. So this is much, much, much more transparent than typical window glass, let's say. Okay? If you could have this in the ocean, you could see the bottom of the ocean very clearly just from the boat on top. It would be very, very transparent indeed. Okay? Another amazing thing that physicists have done is build, optical sources like lasers and optical means of modulation, Mach-Zehnder modulators and other means of modulation. And another remarkable technology is optical amplifiers, which can amplify the signal all optically without conversion to and from the electrical domain. So you can send an optical signal here and send it around the world without transforming it into electrical signal on the way. Okay, so all these things are amazing technologies, but they're all relatively mature now. We haven't seen a huge advance in laser sources or in modulator technology and so on for a while, a decade or so. And so now it's time for information theorists to come in and squeeze the last few bits per second per hertz or whatever out of this type of channel. Okay? So finally, optical communication engineers have decided that just turning things on and off quickly just doesn't cut it anymore. And we need more sophisticated coding and modulation kind of ideas. Okay? So fiber optic communication systems in the industry demand a very high reliability, 10 to the minus 15 probability of error, okay, which makes software simulation kind of a no-go right from the very beginning. We pretty much need hardware or analysis to prove out such a high reliability. Fiber optic communications really challenges electronics. 100 gigabit per second per wavelength rates are very commonplace in the industry today, with rates pushing to 200 to 400 gigabits per second in the next few, in the evolution of fiber optic equipment. This is per wavelength channel data rates. So you need to process bits extremely rapidly. What makes it interesting from an information-theoretic perspective, and that's really why I'm interested in this channel, is that the fiber optic channel is nonlinear. It's a nonlinear channel, which makes it extremely interesting, or let's say extremely challenging to try to work with from an information theory point of view. And this nonlinearity comes about from something called the Kerr Effect. So Kerr was named after this guy Kerr, who discovered that if you have some dielectric material and you expose this material to some external electric field, then the index of refraction of that material changes in response to the external applied field. This is something called the Kerr Effect. Every material has this to some extent. In fact, in fibers, you're not shining an external field. It's the light that you're propagating in the fiber itself that's causing instantaneous changes in the electric field. And this causes changes in the index of refraction. And if you remember your electromagnetics class, many of us would prefer to forget our electromagnetics class. But if you remember the electromagnetics class, you remember that the index of refraction governs the speed of light in the medium, okay? So if you change the index of refraction even a little bit, okay, it's going to change the speed of light. This manifests itself as small changes in the phase of the propagating wave, which can accumulate to large changes of phase over vast distances, like thousands of kilometers. And that makes this whole thing extremely interesting. It also means that traditional concepts of orthogonality, linear orthogonality, that you have in wireless communications, you know that if you send information in one wavelength, but at one carrier frequency, and you have an orthogonal carrier frequency, and with enough band limiting, these two channels don't interact at all, right? We can prove that. But here, because the channel is nonlinear, let's say that we have a really strong optical signal in the red channel over here. This goes ahead and changes the index of refraction of the whole fiber, which then in turn changes the blue channel of interest over here. And so the nonlinearity, this channel is nonlinear, this nonlinearity causes all kinds of crosstalk issues where signals in one wavelength really end up limiting the rates you can achieve in another channel. We cannot really separate these channels cleanly with existing linear methods. That's why we're going to be talking about nonlinear methods like the nonlinear Fourier transform in this talk. So actually, there's a whole host of interesting and complicated PhD topics you could work on and that have been worked on in this sort of alphabet soup of things. You know, things like self-phase modulation, intra-channel phase modulation, cross-phase modulation, intra-channel four-wave mixing. There's a whole bunch of different interactions between the signal and itself, so signal-signal interactions, okay, within the channel or across channels. And of course, noise comes into play because we have amplifiers. These amplifiers are going to create noise, and so there will be interactions between signal and noise. So there's signal-noise interactions. And in fact, noise interacts with itself too, so there will be noise-noise interactions. And so it gets to be quite a complicated mess, actually, quite a mess. So to start to understand this type of thing from an information theory point of view, let's take a very simple kind of model, okay? And really, an optical fiber network is really, we should really be thinking about it from a network information theory point of view, because we have many transmitters, many receivers. We have the ability to add wavelengths and drop them at random points, or at designated points on the fiber. We really should be thinking about it from a network information theory point of view. But that's going to be far too hard. So let's start first of all to think about things with just a single transmitter and a single receiver. So we're going to think about a coherent fiber optic communication system with standard single mode fiber and ideal distributed Raman amplification. What that means is that we can eliminate the effect of loss. We're going to imagine that the channel is ideal and lossless because we have this type of Raman amplification that amplifies the signal as it goes and kind of maintains a constant level. So there is no loss in the fiber. So that 0.2 dB per kilometer will be assumed to be no dB at all per kilometer, just flat. Okay? That's because of the presence of an amplification strategy called Raman amplification. That's not the industry standard. The industry standard is to do lumped amplification with so-called erbium doped fiber amplifiers every 60 to 80 kilometers along a link. So the signal decays in magnitude and then gets amplified and then decays in a periodic way along the, say, 1,000 or 2,000 kilometer transmission path. That's not what we're going to think about. We're going to think about, this perfect distributed amplification system, or we can think about an infinitesimal spacing between lumped amplifiers. That's sort of the idea. And this tends to give us better performance than the lumped strategy. Okay? So we're going to send some kind of signal Q of t at distance 0 and receive some kind of Q of t at distance L. So we're going to measure here time and distance along the fiber using two variables, t and z. So you can tell where I'm from. So Q of t and z is the complex baseband representation of the signal. Okay? So take out the carrier frequency component. Think of the complex baseband representation. The transmitter sends Q of t and 0. The receiver gets to see Q of t and L. And the evolution of Q of t and z is governed by this ugly looking thing here. And it really is a crazy thing. It is a nonlinear stochastic partial differential equation called the nonlinear Schrödinger equation. And it tells you how different physical effects in the fiber interact with one another in order to come up with the overall transmission. Okay? This is actually itself somewhat of an approximation, which is valid in some regimes and is taken to be a very good approximation, so much so that industry uses this model to make fiber designs. But it has its limitations as well. So it's not the ultimate model for the optical fiber, but it's kind of the thing to study in this field. And what it's saying, really this, if you were to sort of turn off noise, so take the noise term to be 0, so 0 forcing term over here, and turn off nonlinearity, this dispersion term would give you kind of the heat equation. Remember, the heat equation is what prompted Fourier to invent Fourier analysis in the first place. Fourier was studying heat evolution along a heated bar. He wanted to see how the temperature profile changed as a function of time, right, over the bar. So this is the dispersion equation. Here in this field, the evolution is along space. It's in the distance dimension. So with respect to the mathematics literature, we exchange x and t. We have here instead z and t, which interchange space and time. So for us, it's spatial evolution instead of temporal evolution. If you go and read literature in this, the mathematicians write it backwards to what fiber optic people do. And nonlinearity, this is this Kerr nonlinearity. That's going to cause changes in the phase. It's going to cause kind of a self-phase modulation of the wave as it propagates along the fiber. Okay? That's what this thing does. And that causes small changes in the angle, in the phase, as we'll also explain in a moment. And this accumulates over distance. So over relatively short distances, the channel is sort of roughly linear. But over long-haul transmission systems, the nonlinearity becomes extremely important. In fact, it is the dominating impairment that industry is struggling with today in terms of DSP algorithms and so on to try to overcome. It's the big problem that's limiting transmission capacity today. And as you know, internet traffic is growing at a rate of sort of 2 dB per year. Okay? So 2 dB per year, if you don't think in dB the way I do, that means about every 5 years is a factor of 10 dB or a factor of 10 in the amount of traffic being exchanged over the internet. Okay? So we need to grow the capacity of our transmission stuff at that rate in order to even just keep pace. So the interesting thing about this channel model is you get a very interesting interaction between noise, nonlinearity, and dispersion. And these are all sort of commingling, coupling together to make a very complicated type of channel model. And even without noise, we don't have simple ways to solve the nonlinear Schrödinger equation. Things are worked on numerically with numerical algorithms. It's really more or less a sort of a finite element method approach. Okay? So what you do, you imagine that the fiber is along, yes?
But in general, do they know a solution exists?
Yes, so you're talking about well-posedness of this, yeah. So yeah.
Maybe a Stokes that you don't even know if it exists.
Yeah, no, here things are well-posed, and you do know that solutions exist, yes. So here, with this numerical method, what you do is you divide the fiber up into many short little segments, and you try to think about how do I propagate this field q of t and z naught to q of t and z naught plus h for this little h. Okay, that's kind of the idea. And if you have distributed amplification, this Raman-style amplification I was talking about, a little bit of noise would be added in our numerical simulations at the end of each of those little segments. Okay? So a 1,000-kilometer transmission span might be divided up into several hundred pieces, or even 1,000 pieces or something of little, whatever 1,000 kilometers divided by 1,000 would be 1 kilometer each, right? That kind of idea, right? And over such a distance, it's short enough that we can sort of handle it numerically. Actually, if you turn the linearity off, the dispersion term off, and just keep the nonlinearity, you have a closed form solution for the nonlinear Schrödinger equation. In fact, you see that the field at distance h is just the field at distance z naught multiplied by a phase factor. Multiplied by a phase factor in time, in the time domain, where the amount of phase rotation depends upon the instantaneous amplitude of the signal at that particular time. So if you were to build a MATLAB implementation of this, you would imagine having many samples in time, and you look at each sample, see what its amplitude is, and then rotate it just a little bit by this appropriate factor over here, okay? Depending on the amplitude. The bigger the amplitude is, the more the rotation is. It's kind of a type of temporal all-pass operation in a sense. Okay, so like the dual of an all-pass filter in signal processing. This is in time here, right? So it's got this unit gain, right? It's redistributing. It's not redistributing in time the amplitudes. It's changing the phase. Okay, that's what's happening in the nonlinear. That's what the nonlinearity is doing. This is the so-called self-phase modulation that's occurring in the fiber. Okay, so if we didn't have dispersion, we could do this nonlinearity in the time domain. It would be very easy to do in an implementation, so we can do that. If you turn off, on the other hand, you flip things and you turn off the nonlinearity and on the dispersion, okay, then you have a linear differential equation, right? Then you just have a linear differential equation, and so you have an LTI type linear system. And you know that the best way to tackle an LTI system is in the frequency domain, right? So take the Fourier transform and multiply by a filter. Now the filter again, it's an all-pass type operation. It's got a quadratic kind of phase response, okay? So if Q tilde here represents the Fourier transform, then what you're doing in the frequency domain again is some kind of all-pass filter type operation. So it's something to do with a change in phase in the frequency domain. Okay, so the amplitudes in the frequency domain now are fixed, and in the frequency those variables are rotating in phase. All of this is energy preserving. You notice there's no loss. Remember, in our model we had no loss, right? So there is an accumulation of energy because at each step we're adding a little bit of noise. So the signal is getting slightly more energetic as we go because of the noise. But if there were no noise, it would be a perfectly noiseless, lossless type of system over here. You can actually show that not only is energy preserved, but entropy is preserved by this type of system. And this allows you to use the entropy power inequality to get a bound on capacity of this type of split-step model. I'll allude to that in a moment. But basically, here's the numerical algorithm. It's called the split-step Fourier method. You do the time domain step. Okay, that's half a step. Then you take the Fourier transform. In the frequency domain, hit that thing with this quadratic phase filter. And then take the inverse Fourier transform. And that's a propagator that propagates the signal over one step over the fiber. And of course, lots of variations on this can be invented. You can adapt the step size for proper convergence and use FFT algorithms to make things go fast. And you can offset the linear and nonlinear steps for better numerical convergence. And there's a whole bunch of tricks. But basically, this is the idea. It's to propagate numerically the signal by doing a linear step separated from a nonlinear step. Okay? And then you can bound the kind of error terms you get by doing this separation. So let's launch a pulse. This looks like something like a sinc function or maybe a raised cosine, something like that. And if you launch this, I'm measuring time in these so-called soliton units, and I'll say more about that later, but some arbitrary time axis over here. And this is the magnitude of Q. Now, this is at 0 kilometers. And then after 200 kilometers and 500 and 1,000, things sort of get kind of weird looking. Okay. And actually, we couldn't even really think, if we wanted to build some kind of equalizer or something, we'd have to sort of think about what the best thing to do here would be. It's not really an obvious thing on what to do to build a detector. You could try to match to this, but then this thing that's being received, but then you'd have to build a different matched filter for 500 kilometers than you would at 1,000 kilometers, which might be a little bit strange. So maybe you'd like to equalize or undo the channel in some way. Sort of one of the state-of-the-art methods that is being proposed, and is kind of thought of as a very high complexity but very effective solution for equalization, is to run the channel backwards at the receiver. In other words, implement this split-step Fourier method, but reverse the sense of space. Okay, run the waveform from the receiver, backwards through the fiber towards the transmitter, using the opposite sign in the z direction. Okay? And that's called digital backpropagation. So run the model backwards. Okay? Now, of course, as people who have studied digital communication systems know, inverting a channel is not necessarily the optimum thing to do, right? It leads to what? What's the problem with inverting the channel? Noise enhancement, exactly. So we don't know that this is necessarily going to be the right thing to do, right? The fact that the channel, that those filters are all passed, though, is helpful because we know there won't be necessarily any particular noise enhancement at one frequency or the other. So this actually works quite effectively, but it's not necessarily provably the optimum detector or optimum equalizer in any sense, okay, that we know. But this does outperform most practical things that people have been building. So if you were to try to look at a capacity estimate based on this receiver, a digital backpropagation receiver, you kind of get a good sense of what you might be able to achieve, at least a bound on what you could achieve in practice. You might get some kind of achievable rate, at least, out of this sort of thing. The other thing that people often do, and always do actually in practice in fibers, is they put different users at different wavelengths. So instead of calling it FDM, the way wireless people do, they call it WDM in optics, wavelength division multiplexing. But it's the same concept. You have a user at channel 1, a different user at channel 2, a different user at channel 3, and so forth. So these users are linearly multiplexed. It's a superposition, a linear superposition of wavelengths separated by some complex exponential modulation, right? Okay, it's the usual idea. And of course, because of the nonlinearity, the channel of interest will be, well, first of all, the nonlinearity causes spectral growth, right? Your own signal will interact with itself and leave its band. Furthermore, everyone else's signal is growing and interfering with you, and so you're going to get all kinds of interference effects. Okay? So, good. So I was, oh yes. Now, you might think that you could try to do, you could numerically simulate, let's say, these 5 channels all back at the receiver and kind of do some kind of multi-user detector, okay? Well, this is actually not really practically possible, even in principle, because what happens in a real network is that you get a user that's, say, transmitting information, let's say, from, I don't know, Detroit to Los Angeles, right? On wavelength that's red, let's say, okay? Now, halfway along in the continent, a blue wavelength is added, which now interferes with this red guy for a while, and then the blue wavelength gets routed somewhere else, okay, down south instead of to the west coast. So the red and the blue interacted in the middle, okay, but they're not co-located at the receiver. So there's no way we can physically possibly do joint processing of the two, okay, even in practice, okay, even in principle, rather. So it's never really done. So typically what people do is they just look at the channel of interest alone and they treat interference as noise. Okay, so that's the typical thing that people do. So what kind of rates can you achieve? Well, one thing you might think about doing is thinking about some kind of, let's say, raised cosine style pulse shapes, some very nice band-limited pulses that satisfy some Nyquist criterion or something. You might try to excite them with some amplitudes and phases. This channel is perfectly phase symmetrical. It treats all phases the same. So any capacity achieving input distribution must be uniform in phase. There's no reason to suspect that 0 degrees phase is somehow preferred over 90 degrees phase or anything. So the only uncertainty might be in the amplitudes. But let's say you confine the amplitudes over some rings and confine the phases over some points within each ring. Okay, excite this type of signal, send it through the optical fiber numerically, right? Model all the effects that we've just been talking about, do the digital backpropagation algorithm at the receiver, okay, and then estimate the mutual information between the input and the output of the channel numerically. What can you get? This was exactly what was done in this paper that was published in 2010 in JLT by Essiambra, Kramer, Windsor, Foschini, and Goebel. So it's this transmitter, okay, some low-pass filter at the receiver that isolates the channel of interest, and this DSP algorithm. This is this backpropagation stuff that I'm talking about. What kind of information rates can you achieve? Very interesting question. Here's the answer. Actually, it's not their answer. My student and I reproduced more or less in a different set of work the same kind of curves. But this is the kind of curve you get. This is the kind of curve you get, which look very strange to a wireless communication engineer. Very strange indeed. Okay? Let me walk you through what these curves are. Okay? First, at the bottom I've labeled it SNR, but actually I should have labeled it launch power. There's no reason to believe that the channel capacity is a function of signal-to-noise ratio, the ratio of the signal power to the noise power. These are two independent things, actually. So in our simulations, the noise power is fixed, and we're varying the launch power. Okay? If you change the noise power, the system behaves differently at high SNR, depending whether you have a high signal and little noise, or the opposite way, right? So it depends, right? Yeah.
So I'm dying to ask, are there good models for the noise in this situation?
Yeah.
So the noise
I neglected to mention the noise model in the stochastic. It's actually white Gaussian is widely accepted. White in time at any particular spatial location, and then independent from spatial location to spatial location. So white in time and space. That seems to be a model that agrees very well with what's actually observed. So it's about as good as it could be from a noise point of view. But then this partial differential equation comes into play and starts to create all these interactions which are tough to deal with.
They do coherent detection?
They do coherent detection these days, yes. yes. Which is actually a comparatively recent innovation, maybe less than a decade in practical commercial systems. Yeah, yeah. And they also have, more or less arbitrary waveform generation capability. So these days you can send more or less any type of pulse that you like. In the old days, people used to work extremely hard just to make an 8 PSK modulation or something like that. They had used all kinds of optical physics tricks to make a constellation. But these days, we can more or less program any waveform that we care for. Yes?
What if you launch solitons?
Ah, good question. We're going to get there. This talk, in the second part of this talk, is about that. Is about soliton transmission. Yes, that is the thing that separates this from a linear thing. And we actually have the possibility of launching solitons. And I think that's very interesting from an information theory point of view. Excellent, excellent question. Yeah?
At the receiver, is there a translation to electrical signals? So
Yes.
there's a detector there.
Yeah, there's a detector that measures the field, does the coherent, you get phase information. Then there's a very high-speed A to D conversion, and then everything is going DSP at that point. That DSP between the DSP equalizing and error-correcting coding, that thing is a big chip. It looks about this big physically, and it has on it heat sinks. It's very hot. It gets very hot. This is per wavelength, okay? And now we have maybe a few hundred wavelengths in a particular box. And so you need a small, nuclear power plant right beside the apparatus.
I missed the beginning of your talk. What rates are we talking about here?
We're talking in deployed systems today, 100 gigabits per second per wavelength. Okay, but that's already today's systems. The ones that people are talking about in research are 200 to 400 G, and going up. Okay, and we're talking about dual polarized, higher order modulation, 64 QAM. This sort of thing is what people are trying to think about going forward. All right. So let me walk you through this slide, okay? Because I think it's really, really telling. So this is launch power. So the signal gets more energetic as we go to the right. And this is achievable rate. Spectral efficiency I wrote, but it's really some kind of achievable rate. This bound here is the bound that corresponds to the corresponding AWGN channel. This will be the AWGN channel at the same signal-to-noise ratio. Okay? And here I've plotted 3 different transmission distances. The one with the lower achievable rate is longer, and the one with the higher achievable rate is shorter. So this one is 500 kilometers, and this one is 2,000 kilometers. Okay? So there's 3 of them altogether. The green curve's the better one, right, is what you get with digital back propagation. So that's the full-blown best equalizer we know how to build sort of thing. Okay? The blue curve is kind of a suboptimal equalizer that you get just by doing a linear equalization, sort of one backwards linear step of just looking at the phase channel. Okay? One big linear step backwards, right from the receiver back to the transmitter. Okay, so the achievable rate is a little bit, half a bit or so better with the full-blown algorithm, but not actually significantly bigger. But what's interesting is that these curves go down. So information theorists in the room, should mutual information go down? So Sandeep is shaking his head. Dave so it shouldn't go down. Why? Why is that?
I think this is taking into account the receiver as well, right?
Yes, the receiver is kind of part of the model here.
Right.
Yeah. Yeah.
So there may be nonlinearities that are entering there.
Yeah.
High
Yeah.
power, right?
Yeah. Yeah.
So this reminds me kind of the opposite curves that we have seen in non-coherent detection where there is an optimal.
Yeah. An optimal launch power or something.
Right, right.
Yeah. Yeah. That's right. So I mean, depending how you set up the capacity or achievable rate problem, right? If you increase a resource, right, I give you more dollars, right? You shouldn't have to do worse. Just don't spend the dollars if you don't want to, right? So it's not going to go down, right? Obviously, right? So increasing launch power, it should at least level off. It shouldn't go down. And what's happening actually is this is a multi-user system. We're looking at the channel of interest in a WDM. And what's happening is we're increasing the power of every user in the system simultaneously. And it's exactly the nonlinearity that's causing extra induced interference noise coming into play. So at high launch power, we're getting this much more interference noise coming into the system. And that's causing the signal to drop like this. And over here, the launch power is so low that the nonlinearity hardly comes into play. And so this system is completely noise limited, okay? And not power limited at all. It's completely just an AWGN style channel, and therefore that's why the Gaussian channel capacity is the dominating performance. So in a sort of a cartoon, this is more or less how things sort of work in this optical business. People sort of seek this optimal launch power where they optimize some criterion, maybe the received OS&R, optical signal-to-noise ratio or something, and they tune the transmitter power until they find the sweet spot, and then they transmit at that particular optical power. If they go higher than that, then there's too much nonlinearity noise induced, and they don't want to do that. Okay? So it seems like this nonlinearity noise business is a dominating impairment in this type of transmission system. Okay.
So why can't we account for the interference? Because at that point it's essentially interference limited.
Yeah, we can't, because remember that we don't have the ability to, well.
I mean, in that example that you said,
Yeah.
it is very similar to interference channel, where the other user is interfering with you, whether it is partly through the channel or at the end of the channel, it doesn't matter.
Yeah, that's true. So perhaps some interference alignment ideas or something. I don't know, but it's an interference type channel. Exactly. Okay. So actually,
It's the nonlinearity that prevents you from doing interference subtraction.
it's some linear idea will not be the right thing to do here. Exactly. So it's not a superposition necessarily, a simple superposition, because the interfering signal is interacting with me as I'm propagating along, as the signal is propagating along the fiber. Okay, so it's not quite as simple as an additive interferer, okay, as in the interference channel. So in a sense, this is kind of like the map of the world in fiber optic communications, So we have the continents that are known. Remember, in maps before the world was explored, there was this sort of gray region where people didn't know what was going on. And that's this gray area over here. So in recent work, we found that actually the AWGN channel capacity is an upper bound for a fiber optic channel, or at least a split-step Fourier model. And so AWGN upper bound exists. You can't exceed this under some reasonable hypothesis. Various lower bounds all have that form of going up and then coming down again. Those are the achievable rates. Okay? At some point, if you put too much power into a fiber, the fiber melts. There are some really cool YouTube videos you can see about something called fiber fuse, where people put a lot of power into an optical fiber, and then the fiber sort of starts glowing, and this fuse goes. I don't know if you've watched cartoons, but there's always like the bad guy with the bomb, right? And then there's this thing that goes shh, and this goes along the fiber, right? This bright light going out. So fiber fuse is great for YouTube, but if you're AT&T and you just spent $1 billion running a fiber, you don't want fiber fuse to happen. Okay, this is not a funny problem; it's a serious one. Okay, so you don't want to get anywhere near this place where the fiber starts to melt. Okay? So there's this uncertain region. We don't know the capacity of the fiber, and that's really an interesting information theory problem. So I see that I have only about 10 minutes left, because all these wonderful questions were that I've been receiving. So I'm going to try to give you sort of a high-level overview of this nonlinear Fourier transform stuff. Okay? I'm going to have to, because because time is running short, I'm going to have to necessitate skipping a few things. Okay, so don't worry. I'll be around later to answer questions. But also, the slides I've sent to Professor Neuhoff and I was going to say Neuhoff, and he'll be able to give them to you. Okay. So part 2 of this talk is to ask this question: does the fiber nonlinearity really place an upper limit on achievable spectral efficiency? And we have to understand the nonlinearity more deeply. And we are not going to give a satisfactory answer, unfortunately. Okay, I think it's still very much an open question and a question for future work. So the nonlinear Schrödinger equation is an example of an evolution equation, a partial differential equation in 1 + 1 dimensions. 1 time dimension, 1 space dimension. Okay, so physicists talk about, maybe 1 + 3 dimensions, time and 3 spatial dimensions. We're going to talk about 1 + 1, 1 spatial dimension. There's not much happening except in the z direction. The x, y direction, nothing is happening very much. Okay. You can actually, by an appropriate normalization, you can change the nonlinear Schrödinger equation and get all the physical parameters to drop out. And you get these so-called soliton units. So we're going to study this sort of nice dimensionless version of the nonlinear Schrödinger equation. And the key idea that we want to do is to encode information in something that's held fixed by the channel, some type of invariant. Some type of invariant. And the key idea, and this is probably the deepest, trickiest idea in this whole talk, is what could this invariant possibly be? So it turns out that there's a possibility in studying evolution equations to associate with an evolution equation a linear differential operator whose eigenspectrum is held invariant under the evolution. Kind of a complicated set of words that I just said. So let me try to explain what this is. We're going to try to find an operator, L, whose spectrum is held invariant under the evolution. Okay? So what is the spectrum of an operator? It's a little bit too deep to get into in this lecture today, but all of you are familiar with the concept of the eigenvalues associated with a matrix. Imagine you had a square matrix that is diagonalizable. So you know what that means? It means that that matrix is similar, right, to a diagonal matrix. The eigenvalues appear on the diagonal, and the eigenvectors appear as columns of the similarity transformation. Everybody knows this from linear algebra. Now imagine you had a matrix family where the entries in the matrix are evolving as functions of t and z. Yet, for every choice of t and z, okay, the eigenvalues are constant, okay, of that. All right? So actually, we're going to think only about evolution in the z direction. So we're thinking about a matrix whose entries are a function of z, okay, but whose eigenvalues don't depend on z. Okay? If such a matrix is diagonalizable, then there will always be this constant diagonal in the middle and an evolving similarity transformation. Okay? So we call such a family of matrices an isospectral family. And in operator theoretic terms, there's also an isospectral family of linear operators. So L of z, this matrix, is always similar to this diagonal in the middle over here. Okay? So it's that diagonal, that is the invariant. This is where we're going to try to encode information by studying this type of thing. So it's actually very easy, it's kind of elementary to show that if you assume that you can take derivatives when needed, and you take the derivative with respect to z of such an operator, then it turns out that that derivative can always be written as a kind of a Lie bracket, a commutator bracket between an operator m and this operator L. In other words, the derivative in the z direction is equal to ml minus lm. If you have L that is isospectral, then it always has this decomposition. And the converse is also true. And so we call this ML a lax pair after the mathematician Peter Lax, who invented this concept in the late 1960s. Okay, so associated with this operator associated with an isospectral family is this Lax equation. Okay, now because L and M don't necessarily commute, you can make nonlinear things happen, because the operator L and the operator M can depend parametrically on your signal. And you have Lm minus Ml. Lm can be some polynomial function of the, let's say, or some nonlinear function of the signal Q, and Ml is not the same as, Lm is not the same as Ml. This commutator is not zero identically, right? And so you can see that you're going to have an isospectral flow if and only if the parameters obey some kind of evolution equation. Okay? So that's a bit of a tricky concept, but that's the idea behind the nonlinear Fourier transform that I'll say a few more words about. It turns out that hidden in this are these eigenvectors, right? The similarity transformation. It turns out that the eigenvectors, if we have this isospectral flow, the eigenvectors evolve separately in the time dimension and in the space dimension. They become wonderfully separated. Okay, so we have actually a coupled system of linear differential equations that describe the evolution of the eigenvectors. So this allows us to define something we term as Lax convolution. We can define a system that obeys this type of Lax equation and define an input-output relation between waveforms at the input, waveforms at the output that obey this type of Lax system. Okay, and we call this Lax convolution. Now, the point of the nonlinear Fourier transform is that it changes convolution into, guess what? Multiplication. Okay, just as the ordinary linear Fourier transform changes convolution into multiplication. This is a very complicated type of convolution that I've defined here, but indeed the nonlinear Fourier transform changes it into multiplication. So I'm going to skip now a bunch of slides, but really it was a remarkable breakthrough in 1972 that Zakharov and Shabbat recognized that the nonlinear Schrödinger equation has a Lax pair. It's not so easy to find a Lax pair for a given equation. Okay? It does have one. It's this Zakharov-Shabbat system. If you plug in the L and the M, after some miraculous cancellations, you'll find that you recover the nonlinear Schrödinger equation. And the eigenspace, actually, so let me skip over this. You can actually show that the spectrum will be supported in the complex plane along the real line, along all real values, and at isolated points in the upper half complex plane. It's precisely these isolated points that correspond to solitonic components of the signal. So solitons are captured in this framework by having a non-zero, a non-trivial discrete spectrum. So the spectrum is partially continuous and partially discrete. I'm going to show you the Fourier transform of a rectangle. So this is homework exercise number 1 in your signals and systems class. Only this is the weird nonlinear systems and signals, okay? And so we're going to define a rectangular pulse. And it's very few pulses can we find closed forms, but for this one we can. And here's what it looks like. Here's what it looks like. So at small signal amplitudes, so A is the signal amplitude, this looks like a sinc function. Fourier transform of a rectangle, everybody knows, is a sinc function, right? And in fact, as you increase the amplitude, it stops being a sinc function. It deviates from a sinc function, and a discrete eigenvalue appears in the spectrum. As you increase the energy further and further and further, more and more of these so-called solitonic components will appear in the spectrum. The system will become more and more like a soliton, and the continuous spectrum will deviate away from a sinc type of response. So the nonlinear Fourier transform has all kinds of cool properties, which we'll skip over, you know, Parseval identities and things like that, okay? And it's easy to, well, it's relatively straightforward to show these things. But the main thing is this. If Q2 is Q1 with some kind of lax convolution, then Q2, the output spectrum is just equal to the input spectrum times a filter. Times a filter, this quadratic phase filter. So the input and output spectra are preserved. So here's the same pulse launching thing I had earlier. Here's the spectrum of the input. That's the continuous spectrum. It happened that this particular spectrum has this weird looking continuous spectrum and these two eigenvalues. So at z equals 0, 200, 500, and 1,000, these are actually numerical computations we did. I mean, they're indistinguishable, okay, up to the screen resolution. The spectrum is held invariant. The spectrum is invariant. Well, at least the amplitude of the spectrum, okay? There's a phase factor that we're not taking into account. Here's a 3-soliton, so it's a pulse with 3 solitonic components and no continuous spectrum. This is in time, and as it evolves, it does weird things, but the spectrum is completely held invariant. So if the spectrum is held invariant, let's put the information in the spectrum. That's the idea, okay? Here's our idea, okay, nonlinear FDM. So let me, if you can just bear with me for 2 more minutes, okay? Is it okay?
Yeah.
Yeah, okay. Then so actually, you know, we thought about this sort of around, well, now it's probably 5-6 years ago. And then later, after we submitted papers and so on, we discovered that Hasegawa and Yu had come up with something very similar called eigenvalue communication, published in 1993 already. Not quite as elaborate as our treatment, but still the key idea was already there. In other words, encode the information in the eigenspectrum of the lax operator. That idea was present already in this 1993 paper. And you know, contemporaneously with us, a student of Meir Feder and Mark Steif at Tel Aviv also worked out some similar concepts, okay? So we started practical work by studying the special case where the continuous spectrum is 0, is absent, and we have only a discrete spectrum. And we call such a signal a multi-soliton, okay? And so there's a whole bunch of interesting numerical issues and algorithms that were needed to be invented to generate things and so on. I won't bore you with the details. But you can sort of first of all think about you know, the simplest kind of modem you might want to build. The first voice band modems were frequency shift keyed, you know. You could turn on a particular tone or not, or you know. Same thing here. You could think about eigenvalue modulation, turning on a tone or off, right? And that's the kind of idea we had over here. But you know, spectral efficiency drops, and then we figured out how to improve that. We were able to make multi-soliton communication just exciting the position of the eigenvalues, not exciting all the possible degrees of freedom. We were able to get something that achieves, you know, spectral efficiency of sort of 3 bits per second per hertz, which, you know, if you look at sort of classical soliton literature, you know, they were getting sort of a spectral efficiencies of 1/10 of a bit per second per hertz, that sort of number. So this seems like a, you know, a big win compared to that. Even with the simplest, you know, not exploiting all the degrees of freedom that you can have. Then our colleagues in Hong Kong built an experiment for us, and we launched some signals. Here's the 4 eigenvalue communication, which we were able to achieve successfully over 300 kilometers. Here are all the possible, well, there's off, but then there's 15 possible on, you know, in all the different combinations. These are the received constellations. We were able to completely successfully, in all cases, decode with no errors. There was absolutely no error at all. Kind of a little bit embarrassing. I can't show a probability of error. There's no error. So, and with 3 eigenvalues, we went much farther to 1,800 kilometers, and were able to decode quite successfully. Recently, just this year, my former student Yosefi, with his student now, my grad student, demonstrated that they could achieve with numerical experiments they could sort of break that remember those curves from before, right? So what they did was they compared sort of a WDM type setup with this type of nonlinear division multiplexing. And they were able to show that even at the point where the WDM starts to drop off, this system keeps going. Okay? Eventually, though, we expect the growth rate will slow. Asymptotically, I expect that we're going to get something like log of the SNR growth rate kind of thing, something like a fading channel type of asymptotic thing. The capacity will not drop, but it will grow at a really slow rate. It will more or less flatten out at some SNR. Okay, so I want to just mention that there's many open problems. Please, you're more than welcome to join if you're interested. Lots of work going on in numerical algorithms and experimental demonstrations, and using the nonlinear Fourier transform as a detector. I want to just stop with this quote. So in 2006, the Steele Prize was given to these mathematicians here, Gardner, Green, Kruskal, Miura. So the Steele Prize is given by the American Mathematical Society. It's a big prize given to sort of career-defining contributions. Okay, and these guys got the prize for inventing the mathematical framework I've been talking about in this talk. Okay, and in the write-up, in the notes that the citation, it said that because of their work, nonlinearity has undergone a revolution from a nuisance to be eliminated to a new tool to be exploited. And I think that's the philosophy that I wanted to share with you today. So I'll stop here. Thank you very much.
It hasn't been easy. Whoa! The robot falls, it breaks.